Okay, so the next item here, which is Bayesian networks. So before that, I want to talk about probabilistic graphical models. These are called PGMs. So what are PGMs? They are a way to define the structure of variable interaction in a probability model, where you define this interaction using graphs, and you have nodes and edges in these graphs. These probabilistic graphical models are useful for human visualization understanding so that you can visually see how the variables interact with each other and how samples are generated. So consider an environment with n variables. We just label them x1 to xn. You could have a probabilistic graphical model that is represented by a graph G1 with vertices and edges. The vertices represent the variables, and the edges represent the relationship or the interaction among the variables. You could also, for the same set of variables from x1 to xn, right, you can construct another graph for it. The v1 and v2 here are the same. However, the edges are different, right? They're still the same variable nodes, but the edges may be different to represent different interaction. So the idea with these PGMs is that our nodes will be the variables and the edges will be the interaction among the variables. And this can be constructed, how you construct the interaction and the edges using the domain knowledge about the problem. So you handcraft these. We also have algorithms that exist that, given data set for your problem, these samples from your variables, it is able to learn a very good graph to represent the relationship among the variables. What are the types of PGMs? You have undirected PGMs. In this case, the edges are undirected, and so they indicate correlation between the variables. You have directed PGMs where you have directed edges where they indicate causality, meaning if you have xi node pointing to another node in your graph, what you're saying is that xi causes xj, or xj is influenced directly by xi. And finally, we have Bayesian networks. These are directed PGMs. However, they are acyclic graphs, meaning the edges are directed and they indicate causality, but there are no cycles in your graph. And this will be our main focus. So our focus will be on Bayesian networks. So what is a Bayesian network? Here, I showed you an example of a probability model that is represented as a Bayesian network where we have three variables, A, B, and C. So this is a Bayesian network for these three variables. As you can see, you have every node is a variable, and you have directed edges. So what we're saying in this probability model using this Bayesian network is that the variable C is influenced or caused by the variable B and the variable A, right? And from this, the Bayesian network actually gives you the order in which the three variables are sampled. So you can't just sample C. Why? Because in order to sample C, you first need to sample A, then you need to sample B, and then finally you can sample C given what the values of A and B are. Or you could have sampled B, then A, and then C given A and B, right? So the way it's written is that, or from this graph here that we see, first the variable A is sampled according to this probability distribution. The probability of A being true is 50%, and the probability that A is false is 50% as well. The probability that B is true is given by this table here, 0.67. And the probability that B is false is 1 minus 0.67. And then finally, the probability that C is true given that A and B is true is 0.2. The probability that C is true given that A is true and B is false is 0.4, and so on for the remainder of the settings. Okay, so this is how Bayesian networks are represented visually, and they represent the variables in your problem as well as the relationship and how the sampling can be done. One more thing I want to note is one thing you notice about these tables is we can represent them in a compact way, right? So the variable A here just requires one entry to store because we can infer the other entry. Similarly, for every setting of A and B here, we know that the probability that C equals true given a particular setting of A and B is 0.2. And so you can infer the probability that C is false given that A is true and B is true as well. One last thing I want to mention is that this is the joint probability distribution, right? Probability of A and B and C. Assuming this Bayesian network is the one is the correct representation of the relationship among the variables, that means that the joint probability is now broken down into how the sampling is done. So in other words, the probability of A and B and C is broken down into the probability of A times the probability of B times the probability of C given A and B, right? And so the Bayesian network compactly represents the joint probability. Here's another famous toy Bayesian network called the burglary network. You have 5 variables. It is representing the problem where if you're at work and your neighbor John calls you to say that your alarm is ringing, but your neighbor Mary doesn't call. Sometimes the alarm is set by earthquake. Is there a burglar? Right? So you'd like to know the probability of a burglar given some other evidence that occurred. And the alarm here is the alarm of your house, right? And so your alarm is influenced by an earthquake, which may cause it, or it's influenced by a burglary, which may have happened. And if an alarm goes off, you can have that Mary calls you or versus another neighbor John that calls you. Right? So this is a Bayesian network and it shows the 5 variables and how the 5 variables are related. If we had 5 variables, these are all binary variables. If we were going to use the full joint probability table, then we would need 2 to the power of 5, which is 32 parameters, right? 32 probabilities. Whereas with this Bayesian network, how many parameters do I need to store? Well, burglar here just requires 1 parameter. Earthquake requires 1 parameter. For the alarm network, or for the alarm variable is the probability of A given B and E, right? And so how many settings do we have for A and B? We have 2 times 2 because they're binary. So that is a total of 4, right? And so you can see here we have 4 entries. So alarm needs 4. John here needs 2 because it is the probability of John given its parent, which is A. And so there's 2 settings for A here, so it needs 2. And similarly, Mary here needs 2 as well. So in total, we need 1 plus 1 plus 4 plus 2 plus 2, right? This is way less than 32. So a Bayesian network can compactly represent your probability model. In general, we call these tables are called the conditional probability tables, right? Because you have the probability of A conditioned on B and E. So a CPT, which is the conditional probability table for a binary variable xi, that has k binary parents, requires 2 to the power of k rows, right? For every possible setting of the parent. Each row requires 1 entry, which is when your xi is equal to true, because you can infer the probability of xi equals false by just saying 1 minus when xi is equal to true. If each variable has no more than k parents, meaning in your Bayesian network you have n variables, right? And each of these variables cannot have more than k parents, that means that your complete network needs about on times 2 to the power of k entries in terms of parameters or probabilities. Now, this number, compared to the full joint table for n variables, which is 2 to the power of n, this is linear in n, right? Especially if your k, the number of parents that your variable can have, is small. So a Bayesian network can really help with reducing the complexity of the full joint distribution, right? And for the alarm net, it has only just 10 parameters versus 31. It's 32, but then you just need 31. You subtract 1 because this last one can be inferred from the 31s here. So for a general BN, if you have n variables with d possible values for each variable, and every variable can only have k parents, the full joint requires d to the power of n, whereas the Bayesian network requires n times d to the power of k entries, right? These are the space complexities. And so this is linear in n. In terms of semantics, right, the Bayesian network, it encodes the joint distribution as the product of conditional distributions given the parents. And we've seen this with this A, B, and C. So that means that if you have n variables, this is the joint, your Bayesian network encodes it as a product of the probability of the variable xi given the parents in your Bayesian network. And so for the alarm net, the joint probability of all the variables, something like this, can be broken down into the probability of not B multiplied by, we're looking at the network, right? We're consulting the network. It's the probability of B times the probability of E times the probability of A given B and E times the probability of J given A times the probability of M given A. And so if another question you could ask is, this also gives you the order of the sampling. If you wanted to sample a full example, you sample B, then E, then A given B and E, and then J given A, and then M given A. And we'll look at examples of how to sample from a Bayesian network. So Bayesian networks have some nice properties. These are two very well-known properties for Bayesian networks, and we'll look at a more general algorithm to extract properties from a Bayesian network. So from the conditional dependence in Bayesian networks, we get two nice properties. The first property is the following. Every variable is conditionally independent of its non-descendants given its parents. So if you look at this subgraph here, if you look at the variable x, it has two parents, um and u1. And what this is saying is that every variable is conditionally independent of its non-descendants given its parents, right? The descendants of x here in this graph is everything from here, right? It is y1 and everything under it. Those are the descendants. The descendants are العيال وعيال العيال and so on, right? اللي هو الأحفاد وما بعد ذلك الذرية. So what this is saying is that the variable x is independent, is condition, every variable x is conditionally independent of its non-descendants given its parents. That means x given its parents, which is u1 and um, is conditionally independent of its non-descendants. So it's going to be conditionally independent of z and j, z1j, and everything that is above this this purple shaded area here, right? And we'll see why this is helpful when we are trying to solve queries. We'll see where this comes up. Here's another more interesting one, something called the Markov blanket. A node is conditionally independent of all other nodes in the network, given its parents, children, and its children's parents. So if you have a variable x like this, and you are given, its Markov blanket, which are its parents, its children, and its children's parents, which is z1j, then everything else in the network, it will be independent of it, given its Markov blanket. This is called the Markov blanket of a variable. So why are these properties helpful? Well, let's look at this graph here. This is a Bayesian network, right? And let's look at this query here. I won't go into the details. I just want to show you how you can use these properties to, solve these queries in much faster. So here it says, what is the probability of x5 and x6 given x2 and x3? One thing you notice is that every variable is conditionally dependent of its non-descendant given its parents. x6 has the two parents x2 and x3. And these two parents are given in your query. They're here. So we could have written, very simply applied this property and said that x5 is independent of x6 because we're given the parents. So we could have broken down this query very simply into these two queries. All right, x6 given x2 and x3. And we solve for this on its own, and we solve for this on its own, right? This is easy to solve because we just need to consult the conditional probability table here, right? So we could have exploited this rule from Bayesian networks to break down this query early on and solve it, and to solve this problem and then solve this problem. What happens if you don't do that? Well, you're going to do it the long way, right? We're going to break this down into the joint, which is the numerator, right? It's the probability of x5, x2, x6, x2, x3, divided by the probability of x2 and x3. Then, in order to solve this, we need to sum out the hidden variables. So this is summing out the hidden variables in the numerator. These are all the hidden variables for this probability here. And these are all the hidden variables for this probability here. And then, right, you would have taken this full joint distribution here and then looked at your network here. You look at the network and then you break down the joint into the conditional probabilities of the network, right? This is just using the Bayesian network to deconstruct the joint. And then you do the summation here. One thing you notice as well is that there are terms that cancel out. So x1 divided by x1 cancels out. This cancels out here. These two cancel out. This two cancel out. And so many things cancel out. And many terms here, if you do the math, they sum to 1. And actually, all of this work that you're doing very simply simplifies to if you just exploited the rule, right? And so you could do it the long way, or you can just identify that you can exploit the rule and directly go to skip all these steps here. Here's another example with the Markov blanket. What is the probability of x6 given these variables? And one thing you notice that these variables are the Markov blanket of the network. And so you could have done it the long way, right? But you notice that you could have exploited just involving the variables that are in your Markov blanket, and you could have just skipped all this stuff here, right? Here's another more concrete example with the Markov blanket. What is the probability of x11 and x6 given the Markov blanket of x6? So you're given these variables here. Then we already know that x6 is independent of all other variables given its Markov blanket. We could have broken down this entire query into the probability of x6 given its Markov blanket multiplied by the probability of x11 given the evidence that exists. And we could have solved this alone and this alone. And then using that the parents of x11 are given, this is x11 and we are given its parent x9, and so we know that it's independent of everything else in the network here, and so we could have simplified this query as well, right? So these properties are very helpful to simplify the query. It's hard to see it. However, there's a general algorithm that allows you, if you can't memorize the Markov blanket rule or the other rule that I gave, there's actually a more general algorithm to know if your variables are independent or not given some evidence variables. And here is the general algorithm. It's called d-separation. It's a very simple algorithm. And we'll cover this algorithm right now with some examples. So here's d-separation. So there's a more formal algorithm to determine which variables are independent given evidence in a Bayesian network. This is called d-separation. So if you're given a query, the probability of some query variables given some evidence, d-separation works as follows. You want to look at your Bayesian network and draw what's known as the ancestral graph. So construct the ancestral graph of all variables mentioned in the probability expression. So you're going to take your Bayesian network and construct what's known as the ancestral graph. This graph will contain the Bayesian network that just involves the variables that are in your query and your evidence. And this will be a reduced version of the original network. Then from the ancestral graph, you're going to connect the parents. For each pair of variables with a common child, you're going to draw an undirected edge or line between them. Following this, you're going to replace, because your graph in your Bayesian network is directed, you're going to replace the directed edges with undirected edges. And then finally, you're going to delete the evidence variables from your network. So these are the four main steps. And I don't blame you if you don't understand what this is saying. I think it would be better to just show some examples. So here's some examples. So you're given this Bayesian network. It involves these variables that you see here. And here's a question. Are A and B conditionally independent of each other given D and F? So in other words, this is the symbol, right? We're saying, is A independent of B given D and F? Well, let's use the d-separation algorithm. So what I'll need to do is draw the ancestral graph. This is the Bayesian network that just involves A, B, D, and F. And if you inspect your Bayesian network, in order to sample A, I will need to keep it. To sample B, I will need to keep it. But in order to sample F, that means I need to sample D and I need to sample C. And in order to sample D, I guess it already exists in my ancestral graph. So the ancestral graph is the set of all variables that are involved in your query and your evidence that will allow you to sample them all, right? So it is just a subset of the current Bayesian network. And this is the ancestral graph here. That's step one. Step two is the following. We are going to connect parents. So if you look at this Bayesian network here, or this ancestry graph, we see that C has two parents, A and B. I will connect them. D only has one parent, and F has only one parent. So any a node that has two parents, you connect those parents. So connect the parents. Step 3 is make everything undirected. And then step 4, we want to delete from, the step, this graph here, the given evidence, which is DNF. So we're going to delete DNF and all their edges. And we're given this graph here. Okay. Then answer the question, is A, A and B, are they connected in step 4? Yes, there is a connection between them. And so the answer is that if there is a path between A and B, then we cannot confirm or deny if independence hold. If there was no path between A and B, meaning there's no connection or there's no path between A and B, then we can say that yes, A is independent of B given F. So for this case, there is a path between A and B, and so we cannot confirm that A is independent of B given D and F. Here's another example. Is D independent of E given C? Again, we need to include C, we need to include D, and we need to include E. That means we just need this part of the network. So this is the ancestry graph. Sorry, where is D, E, and C? So that's D, E, and C. And we also need to include, in order to sample C, you will need to also sample A and B. So you need to include everything along with what it requires to sample it, right? So this is the ancestry graph. Because we need, in order to sample C, we will need A and B as well. So the ancestry graph is here. Then for every node that has a child, that has parents, we need to connect those parents. So this has two parents, we need to connect these two parents. Finally, remove the undirected edges. Finally, what is your evidence? C. So we will remove C and all its corresponding edges, right? And so we're left with this graph here. And then we answer the question, is there a connection between D and E? No, there isn't. So because there is no path between E and D, we can confirm that the statement is true. So D is independent of E given C. One final example, is D independent of E given no evidence? Again, D, E, and in order to sample them, I need C. And in order to sample C, I will need A and B. All right? Connect the parents, remove the directed edges, and then delete the givens. There's no given here, so nothing is deleted. And so is there a connection or a path between D and E? Yes, there is a path through here. And so because there is a path, we cannot confirm the statement, meaning I cannot confirm is D is independent of E. So just as a recap, you perform to answer whether or not the variables are independent is you will need to follow these 4 steps. After following these 4 steps, at the end, you need to say, is there a path between E and D or the variables? If there is a path, then you cannot confirm the statement. If there is no path, then yes, independence holds. I won't go over these practice. So this is just practice for a Bayesian network. You can expect questions like this in the exam. You're given a Bayesian networks with the corresponding probabilities, and you're asked the question, what is the probability of this query, right? And so these will be incorporated in the slides. I highly encourage you to practice this on your own in order to get a hang for it. But this is definitely something you can expect in the exam. And so maybe we'll cover this one real quick. What is the probability of J? Right? In order to answer this query, I will need to sum out the hidden variables, right? How do I answer the query for the probability of J? Well, I already can tell that in order to answer the probability of J, I will need to sample A. And in order to sample A, I will need to sample B and E. And so I can already tell that I need to sum over the hidden A, B, and E. So if you sum over all the hidden variables, including M, this is what it looks like. Then you need to break down the joint using the Bayesian network. This is probability of B times the probability of E times the probability of A given B and E times the probability of J given A times the probability of M given A. You need to do the summation over all settings of these hidden variables. One thing you notice is I just moved the summation inwards is that look at this summation here. This summation, which is the M here, this is going to sum to 1. And so it's just this big summation here multiplied by the number 1. So you really did not need to do this summation. And hopefully this makes it clear. To answer the probability of J, I just need the part of the network that influences J, just those variables that are involved in sampling J, right? And I could ignore the rest of the network. right? And so you will need to do this summation in order to answer the query. Uh, in order to answer this query, we'll just go over it real quick. We're going to break it down into numerator divided by denominator, right? And so to answer this query, J, B, E, M, and A is very clear, right? Just break down, just to be clear, the probability of B is when B is true, and the probability of lowercase not B is when B is false, right? So this is B is true, E is true, E is true, A is true, and J is true. Whereas for the numerator, I can sum over all the hidden variables in my model, in my network, but it's not needed, to be honest, because the question is, how do I sample A? Well, in order to sample A, I need to sample B and E. That is what influences A. And so I could have skipped this entire process of summing over J and M because it's just going to sum to 1. Right? Look at this, sums to 1, and this also sums to 1. And so I didn't need to do this work. I could have just summed over B and E and that's it, and that part of the network, right? To sum over this part of the network, I need to sample B and then E and then A given B and E. And so hopefully this gives you an idea of how to get a lot of shortcuts when you answer queries, right? And you can do this at home on your own time. There's a very nice package in Python. It's called pgmpy. Maybe we'll do a programming assignment 3 with this package as well. But this package allows you to construct Bayesian networks. We'll show some examples of this in class, inshallah, where we are going to construct this network over here and answer queries using this package. So it allows you to construct a network, add the conditional probability table probabilities, and then also answer queries for using this network. One last thing I want to mention is how do we construct the structure of a Bayesian network? We really won't go into details on this because there's algorithms that do this and they're rather involved. Just know the following. How many possible graphs are there for n variables? Meaning if you had n variables, n nodes, right? You had n possible nodes. How many ways can you construct a graph? Meaning how many edges can you construct or possible graphs can you construct? The short answer is that this is exponential. There's an exponential number of graphs if you have n variables. The other one is how to find the optimal Bayesian network structure. This is an NP hard problem, and so it is not easy to find the optimal Bayesian network structure. However, this is finding the optimal network is NP hard. However, domain knowledge can be used to construct the network directly. For example, if you're working on a medical problem, maybe you know that some variables influence some other variables in your problem, right? Using your domain knowledge. Maybe you have a disease, and this disease influences symptoms, or maybe vice versa. In practice, we can also use algorithms guided by heuristics. So if you go to the pgmpy package, it has these structure learning algorithms. And these algorithms here are all search type of algorithms, like we learned in local search, where they try to construct a structure that based off of data. And it tries to find a reasonably compact network. Right, so we won't cover these topics in this course. I just thought to give you a nice, some notes and some guidance if you are interested in this topic. And the structure of your network can really influence the size or how compact the network is. Like for the alarm network, we could have constructed this Bayesian network structure or this Bayesian network structure. And actually, if you notice in this Bayesian network, there's a lot of connections, and so the number of parameters that you need here is, so the number of parameters for this one is 13, whereas the number of parameters for this one is 31. So with this structure here, you really didn't get any savings. This is like the full joint probability table. And so the structure of the network really does impact the size. And just to recap, all the assumptions that we talked about so far. So we looked at the full joint table, and then this is with no assumptions. Then we looked at if you make independent assumptions. Then we looked at if you made some types of conditional dependent assumptions. Then we looked at general Bayesian networks that you can handcraft on your own. All of these assumptions that you make can be visualized as a Bayesian network. Just to convince you, suppose we have n binary variables. With no assumptions, we have a full joint table with 2 to the power of n entries. This is a Bayesian network that is completely connected. That means all nodes are connected to all other nodes. If we assume all variables are independent of each other, then this is a Bayesian network with no edges, right? All nodes have no connections. This is the Bayesian network if you assume that there is no if you assume independence among all the variables, right? There's no connections, meaning there's no relationship among the variables. If we assume that xi is influenced by xi minus 1, then we get a tree-like Bayesian network, right? This assumption here is this structure as a Bayesian network. So a Bayesian network structure is determined by the assumptions we make about the variable relationship. Typically, this is decided by domain knowledge, or we can construct it using algorithms like I mentioned. What about for a naive Bayes assumption? Consider a naive Bayes assumption where k different symptom variables, x1 to xk, are conditionally independent of each other given the disease. That means, this joint probability given the disease can be broken down into, right? They're conditionally independent of each other given the disease. We can break it down into these products. As a Bayesian network, this is what it looks like, right? These variables are conditionally independent of each other given the disease. The disease is what influences these variables, and each variable is influenced by the disease alone. And you can see there's no interaction among the variables, right? So this naive Bayes assumption is this Bayesian network. I just wanted to show you examples for more general problems, how Bayesian networks can be used. So this is an example from the book of whether or not to approve car insurance claims for car accidents, right? And there's a lot of information that goes into this, like how many accidents did the driver have, what is the car value, how old is the car, and how many how much damage did the car have, and so on, and what is the driving behavior, and so on. This is the Bayesian network to determine if the car won't stop. We're interested in this variable. Will the car start? Well, the car starting has a lot of is influenced by, is there gas? Is there no oil? What is the battery age, and so on. This is a large network that shows, liver disease. We're interested in predicting the probability of there being a liver disorder, and this is influenced by a lot of patient history. This is a Bayesian network that was used by Microsoft. I'm unsure if they still use this, but this is the Bayesian network that was used a while back for determining if the printer faults. So what kind of issue is there with your printer? So there's a lot of use cases for this. And then, inshallah, in class, I won't go into the details of this, but in class, we'll go over it, inshallah. I'll show you how to use a Bayesian network with the pit world example, and how we can use the Bayesian network to make progress and use probability to weigh the risk of our actions. So I won't go into detail here, but we'll go over it, inshallah, in class, and we'll use, inshallah, the PGMPY package to showcase this. So I'll skip this, inshallah, and cover it in class. Okay, now we gave a nice overview of Bayesian networks. They have a lot of nice properties, and they allow us to represent things compactly. And we looked at how to answer queries, at least in terms of, if I give you a query in a Bayesian network, you know how to do it by hand. What I want to talk about right now is there an algorithm to do this for us? Right? If you are given a Bayesian network and you want to answer a query using an algorithm, what is the time complexity of this algorithm, and how fast can we make this algorithm go? So we won't really go into details on this, but about 3 slides to cover this. So how do I inform inference? If you remember, inference is answering a query. What is the probability of Q given E? We looked at with the full joint distribution table. It gives me all information I need to compute any event. However, I'm going to pay the cost that the time complexity of inference is going to be 2 to the power of n in the worst case. With a Bayesian network, we saw that a Bayesian network compactly represents the full joint table, meaning that my space complexity with a Bayesian network is linear in the number of variables. If you remember, it's this ON d to the power of k. This is the space complexity. The question now is, what is the time complexity of answering a query in a Bayesian network? Is it still linear? Let's see. Imagine I give you this Bayesian network here, a simple one. and I want to answer this query, the probability of B given J and M. In order to answer this query, I need to sum over the hidden. The hidden variables here are E and A, and so I need to compute this query, right? So you can see here that we have to add 4 terms, 2 for E and 2 for A, right? Because I have 2 values for A. So the 4 terms are this. I need to sum this term. I need to sum 4 of them, 2 for A and 2 for E, each with 5 multiplications. In the worst case, right, we have to sum over n minus 1 hidden variables. So that means I will do summation over x1, x2, all the way up to xn minus 1, right? Because those are all hidden. And so I need to sum over O2 to the power of n sum, each a product of n terms. That means the total worst case time complexity is going to be On times 2 to the power of n. That's more work than the full joint table. If you remember, the full joint table time complexity is O2 to the power of n. Where am I getting this n? Well, you're getting this n mainly because, if you remember, the full joint works on these entries, right? Whereas the n term here is because you breaking down, having to do these multiplications. How do I remove this n term? Well, we can get rid of the n by rearranging terms. So if you remember, this is my Bayesian network summation. I'm summing 4 terms here, and I need to do 5 multiplication. I want to reduce the number of multiplications. Just move the summation inward, right? So I'll just move the summation inward, where E is here, and then A is here. If I move it inward, then with this, I can get away with a fewer number of multiplications. And actually, if you look at this summation that I'm doing here, I can break it down into what's known as the compute tree for my query. So if you notice, there's a probability of B at the start. This is here. And then I need to sum 2 settings for E. So the left path is when E is true, and the right path is when E is false. And then for each of those paths, I will need to try when A is true and A is false. So this is when A is true. So this is E true, A true. This is E true, A false. Whereas this is false for E, and then A is true, and this is A is false, right? So I have broken down the graph into these 2 terms, or into this. So this query, this is the compute graph for it. The reason I wanted to show the compute graph is because, okay, in order to remove the n term, I can remove the summation inward. But that's still going to just remove the n term, and I still have exponential. I have O2 to the power of n. It is still an exponential time complexity to compute this query. From the compute graph, one thing I notice about the compute graph is that look at this part here and look at this part here. One thing you notice is that these 2 paths here are doing the same thing, right? You're multiplying 0.7 by 0.9. Here you're multiplying 0.7 by 0.9. I don't need to do this multiplication. I could have done it once, saved this computation, and reused it here. What about this path here? I do this computation once, and I could have saved it for this path here. I don't need to redo it, right? So the idea is that in a complex query, there's a lot of, especially using a Bayesian network, there's a lot of things that could be computed once, stored somewhere, and then reuse those computations. And this reusing of computation reminds you of something you learned in analysis of algorithms, which is dynamic programming, right? So can we do better than exponential time? If you look at the computation tree, you can see that some products are computed more than once. The key to efficient Bayesian networks is to avoid these recomputations. So I could store computations and reuse them, so I can use dynamic programming for this. I won't go into the details of how this is done, but there is an algorithm that does this. So there's an algorithm that is used for exact inference in Bayesian networks that uses dynamic programming. This is called variable elimination algorithm. It is a dynamic programming-like approach. It avoids recomputation. We won't go into the details. You can see this video for those interested. For this course, you just need to know the following. The worst case time complexity of exact inference in Bayesian network is OD to the power of n. There's an algorithm called variable elimination algorithm that is used for exact inference. It is a dynamic programming approach. Its worst case is still OD to the power of n. However, in practice, it does well. The average case for it works well in practice. It's not always guaranteed to not be exponential. However, for the majority of cases, it is going to be less than exponential and fast in terms of computation. So you just need to know the name of the algorithm and that it works well in practice, but the worst case will always be exponential time complexity. Um, one last thing is that for the burglar network that you see here, you can see that there is at most one path between any two nodes. So if you look at like the node B here and the node M, there's only one path between them. The node E here and the node B, there's only one path between them. Whereas in this graph here that you see here, if you take the node C and the node W, for example, there's two paths. There's one through R and one through S. So networks where there is at most one path between any two nodes is called a singly connected network, or a polytree. The time complexity for such singly connected networks for exact inference is linear in the size of the network. So that means it is going to cost you OND to the power of k. And this can be done using variable elimination with a particular ordering that is efficient for polytrees. And the interesting part is many Bayesian networks can be when you try to construct them using domain knowledge, it just so happens that they are going to be polytrees. So this is helpful for us because it tells us that using the variable elimination algorithm will help us with these polytree types networks. We can solve it in less than exponential in the number of variables. Whereas for multiply connected networks, which is the general case or the worst case for BNs, it is NP hard to do exact inference. There is no known efficient algorithm. Worst case is D to the power of n. So in the worst case, even if you apply variable elimination for these multiply connected networks, it will be exponential time complexity to answer the queries for it. So that's all I'm going to say for exact inference in Bayesian networks. There is no known efficient algorithm for the general case. However, variable elimination, which is a dynamic programming approach, does well on average. The last topic we will talk about is approximate inference, which is in Bayesian networks, we cannot do less than exponential for the general case exact inference. However, we can do approximate inference. So exact inference in Bayesian networks is intractable in general. However, can we do approximate inference? Approximate inference in Bayesian networks uses random sampling to compute approximate answers. The more samples we generate, the more accurate the answer is going to be. Random sampling algorithms are called Monte Carlo algorithms. Two main families of sampling algorithms. Direct sampling algorithms. These are called prior sampling, rejection sampling, and likelihood weighting. This is the three sampling algorithms that we'll talk about. Other types are called Markov chain sampling algorithms. These are called, two of them are MCMC and another one's called Gibbs sampling. These are more advanced approximate sampling algorithms. However, we won't cover them in this class. So we'll just take the direct ones for this intro course. These three ones. Prior, then we'll talk about rejection, and then likelihood weighting. We'll discuss these three direct sampling, and in exact, what we're going to do is, if we're given a query, how can we use these three algorithms in order to approximate? We want to find an approximation, right? We want to answer this query with an approximate answer, not an exact answer. And these approximate inference algorithms, hopefully they run in less than exponential time complexity. I'm not going to go to the detail, but this is just a reminder of discrete variable sampling. If you have a discrete variable C, like the colors red, green, and blue, and you have a probability over it, then if you remember, this slide just gives you a reminder of how to perform sampling from this discrete variable, because this is what we're going to do. We're going to sample samples from our Bayesian network. So consider this Bayesian network here. You're given three variables: cloudy, sprinkler, rain, and wet grass. Assume these variables are all binary. And this is the Bayesian network for this model. How can we do prior sampling? So in prior sampling, we sample from a Bayesian network based on its structure. You sample the variable with no parents first, and then sample the variable as their evidence becomes available, the remainder variables. So with this Bayesian networks, there's actually two ways to sample. I could sample cloudy, and then after sampling cloudy, I can sample sprinkler, rain, and then wet grass. Or I can sample cloudy, rain, sprinkler, and then wet grass, right? So the order starts is you start with variables that have no parents and then sample the remainder variables as the parents become available. Okay, how do I sample from this network? Very simply, just sample numbers for you, and then sample from the network based off of the order of the Bayesian network. So imagine I sampled 0.35 and I want to sample from this Bayesian network. I'm going to use the order cloudy, sprinkler, rain, and then wet grass. So from 0.35, remember we broke down these two settings for the cloudy. This is when cloudy is true. This is when cloudy is false. And remember, I use the real number line from 0 to 1. And then I will say that, you know, if it's from 0 to 0.5, this is when cloudy is true. And then from 0.5 to 1, this is when cloudy is false, right? So I got 0.35. This falls in this range here. And so for the first sample, I'm going to sample C for this first variable, C. And then for rain, in order to sample rain, I've already sampled C equals true, so I'm operating in this bracket here, right? And so when I operate in this bracket, actually the order I'm going to use is sample sprinkler first. So I'm going to sample this one first. So I'm operating in this bracket when C equals true. And then I get a 0.7. And if you look at 0.7, 0.7 falls in this range here. And so I'm going to sample not S. Now I'm going to sample rain. I have 0.15. 0.15 falls in this range here between 0 and 0.8. So now I've sampled R. And then finally, I have 0.85. I'm at wet grass, right? But which bracket am I operating in? I'm operating when C is true, when not S and R, right? So not S and R. So I'm in this bracket here, right? And I have 0.85. 0.85 falls in the first bin here. So I've sampled W. So it's my first sample using these numbers for you is C, not S, R, and W. C, not S, R, and W. What about for these variables or these numbers here for you? I'll just do the first one. When U is 0.9, then it falls in this bracket. So I sampled not C, right? And then not C for the sprinkler falls in this bracket. I get 0.25, so that's S. And then not C is in this bracket for R. I get 0.42, which is in this bracket here, this bin here. So this is not R. And then finally, S and not R is this bracket here. And then I get 0.55, which is the first bin. So that's a W. So it's not S, not C, S, not R, and W. Right? Not C, S, not R, and W. And that is how you do direct sampling from a Bayesian network, right? Using the U values. You follow the structure of the network and you sample parents followed by children given the parents. Right? And this is how to do the sampling as an algorithm. Okay. How can I use prior sampling or direct sampling in order to approximate queries? Imagine you had this Bayesian network and you want to answer this following query. What is the probability of not S given R and W? In order to answer this query using prior sampling algorithm, what we do is that I'm going to sample samples from the network. Let's say I have enough time to sample these samples that you see here. This is 1, 2, 3, 4, and 5. Right? I sampled these 5 samples. Now I can answer this query using approximation. How am I going to do it? What is the probability of not S given R and W? Very simply, I grab the samples that is consistent with the evidence. These are this sample, we have R and W here. We also have this sample. This is not a valid sample because this is not consistent with the evidence. This is a valid sample and this is not a valid sample. So I have these 3 samples that are consistent with the evidence. Then among these samples, how many have the not S? Well, this sample has it, this one doesn't, and this one has it as well, right? So I have 2 out of 3 of these samples are consistent with the evidence, right? So you can see here, among these samples, how many have the not S? It is 2 out of 3. And so using approximation, this query is approximated by 2 over 3 using my samples, right? The reason it's an approximation is because I need to sample a lot of samples to get an even better approximation, right? So depending on how many samples I have, I'll get a better approximation to the query. And this is how you use prior sampling. Prior sampling samples full samples. I sample as many as I can given my budget or how much time I have. And then after I do all those samples, I will then approximate the query as such. Here's another example. I still have my 5 samples here. What is the probability of W? Very simply, this has no evidence, so I'm going to consider all the samples. So here I have 5 examples. How many of these samples are consistent with W? I have 1, 2, 3, 4. So 4 out of 5, right? And so the approximation is 4 out of 5. And this will get closer to the exact answer the more samples I have. So this is prior sampling. The other sampling algorithm is called rejection sampling. So rejection sampling is on-the-fly application of prior sampling for estimating conditional probabilities. So how does it work? Let's say we want to compute the probability of C given not S and R. The idea with the rejection sampling versus prior sampling is that as we generate samples using, the numbers U, samples with S or not R are not relevant. These are rejected or discarded on the fly because we're trying to generate samples that are consistent with this evidence. So if we are generating samples and we generate S or not R, these samples are not consistent with the evidence. We directly stop generation and we move on to the next sample. Whereas prior sampling will generate N samples completely. So you do the full sampling for all samples completely, and then rejection sampling, and then you ignore the samples that are not consistent with the evidence. Whereas rejection sampling will discard inconsistent sampling as it generates them. That is the main difference between prior and rejection. So rejection sampling can be used to generate N samples consistent with the evidence, making use of all N samples for approximating the conditional query. Prior sampling generates N samples, but many of them may not be consistent with the evidence. Whereas rejection sampling is going to generate N samples that are exactly consistent with the evidence. Just to show you what I mean by this, as if I'm trying to generate samples for this one using rejection sampling, I generate this sample. This is fine because we have not S and R. However, as I generate the next sample, I generate C, right? I'm going to generate C first. And then if I generate S and my S is, this S, then there's no need to continue because this S is inconsistent with the evidence. So I stop generating here and I move on to the next sample, right? This is fine. But then if I go here and I generate not S and then not R, I stop. I reject the sample and move on to the next. That is how rejection sampling works. Whereas in prior sampling, I would have continued to generate all the samples completely, and then I rejected these samples afterward. Right? So rejection sampling is on-the-fly application of prior sampling. That's the main difference. This is just the algorithm for it. Right? If xi is not consistent with the evidence, then I stop the generation of the sample. Okay. The final algorithm, which is likelihood weighing. This is an interesting algorithm. We'll try to show an example. We'll show an example just to make it clear. So what are the problems with rejection sampling? The problem with rejection sampling is that if the evidence variables are unlikely, then you're going to reject a lot of samples. And if you're trying to generate, let's say, 1,000 samples, and the evidence is very unlikely, then as you're trying to generate 1,000 samples, it'll take you a long time to generate 1,000 samples that are consistent with the unlikely evidence, right? Because you're going to reject so many samples that are not consistent with the evidence. And so the probability of the evidence drops exponentially as the number of variables increases. The evidence variables increases. This makes sense, right? If you have a lot of evidence variables, the likelihood for it is going to drop. So to get good approximation, it may require a large number of samples, particularly if evidence is rare. And so just as an example, imagine you had a very simple Bayesian network, and you're trying to approximate the probability of shape given that the color is blue. But let's say that the color being blue is very rare. And so with rejection sampling, you're going to reject a lot of samples, and you're going to have very few samples that are consistent with the evidence. And so your approximation is not going to be that great. What can we do to fix this? Well, this is where likelihood weighing comes in. Likelihood weighing does the following. It says, hey, let us fix the evidence variables in my samples, and let's sample the remaining variables. The idea works as follows. If I'm trying to answer the query, what is the probability of shape given that the color is blue. The idea is that as I generate samples, I'm going to fix the evidence. The evidence here is blue, and so all my samples that I generate are going to have a fixed setting for the variable color. We're going to set it to blue. We're going to set it to values of the evidence, right? So you can see all my samples here are set to blue. And for example, for the first sample, when I fix this to blue, all I need to do is I just need to sample shape, right? And so I will sample the shape variable given the value blue, right? The problem with this is that after fixing the evidence and sampling the remainder variables, the issue with this is that this is not the same Bayesian network as sampling this, meaning that these samples that you see here are generated from the distribution of the Bayesian network, whereas these samples are not generated from this distribution of the Bayesian network. Why? Because I've fixed the evidence and then I sampled the remainder variables, right? So how do I fix this issue? Right? These samples are not sampled directly from the original Bayesian network. They're sampled from this altered Bayesian network. Very simply, I do what is known as weight correction. Solution: apply a correction to weigh each sample. You weight each sample by the probability of the evidence variables given the parents using the Bayesian network, right? In other words, for this sample here, the weight of this sample is going to be the probability of the evidence, which is blue, given the parents of the evidence. So from this network, the parent of the color is the shape, right? So my weight is going to be the probability of blue given the given pyramid. For this one, it's going to be probability of blue given pyramid. For this one, it's going to be the probability of blue given sphere. And so this weighing here is a correction on the weight of the samples. How does this work in practice? Let's look at a more concrete examples. We go back to to this example, and I want to answer this query using likelihood weighing, right? So again, what do I do? When I generate samples, I'm going to fix the evidence. So let's generate the first sample, right? I fix the evidence, S and W. I need to generate the remainder variables. The remainder variables, I need to generate cloudy first and then rain. Let's say I generated cloudy using U, right? And maybe U was, I don't know, 0.1. 0.1 falls in this range, so I'm going to sample C. And now I need to sample rain, and rain is sampled given C, so I'm in this bracket here, right? And I sampled R using another U and so on. Now I have a full complete sample. I'm not done yet. I need to weigh this sample. When I weigh the sample, I weigh each sample by the probability of the evidence given the parents. So what are the evidence here? The evidence here, if you remember, is from the query. It is S and W. And the way I would start is I would take S first, which is one of my evidence, and I need to weigh this sample by the probability of S given the parents of S. So if you look at here, the parents of S is cloudy. So what is the probability of S, which is S equals true, given that C is equal to true? Looking at this bracket here, the probability that S is true given that C is true is 0.1. So I'm going to multiply this. I'm going to weigh the sample by 0.1. I'm still not done yet. I have another evidence variable, which is W. Now I need to weigh it by the probability of W given the parents of W. So it's the probability of W being true given the parents, which is sprinkler and rain, given S and R. We consult the table. S, R, and W. So I'll need to multiply this by 0.99. And this is what we mean by weigh each sample by the probability of the evidence given the parents. So now this becomes the weight of this sample is 0.099. Let's sample another sample. Here's another sample. One thing you notice is that the evidence is fixed. When I weigh the samples, where did this 0.5 come from? Well, it's the probability of the evidence, S, given its parent, C. If you look at here, this is not C, this is S, this is 0.5, right? So this is where this 0.5 came from. What about 0.9? It came from the probability of W given not R and S. So the probability of W given not R and S. So this is where the 0.9 came from, right? So the weight of this sample is 0.45. And so on for the rest. You do the same thing, fix the evidence, sample the remainder variables, and then weigh accordingly. So let's say I generated these three samples. How do I answer this query? The way I would answer is very simply. The probability of this query is, I break it down into numerator and denominator, right? It is the probability of C and R and S and W divided by the probability of S and W. What is the probability of C, R, S, and W? It is, the weight of all the samples that have C, R, S, and W. So if you look at these samples, which samples have C, R, S, and W? This is one of them. And that's it, right? So the numerator is just 0.099. You can see it here. What about the denominator? The denominator is all the samples that have S and W. So it is this sample. This also has S and W, and this also has S and W. So it is going to be all your samples because we fixed the evidence, right? So I sum over the samples. So one thing you notice is that this reweighing is a way to correct the fact that we fixed the evidence variables in order to reweigh the samples correctly. And now this approximation is an approximation of your original query. Right? So one thing about likelihood weighing is that all samples that you generate, none of them are rejected. All of them are reused. And so this is more efficient as an algorithm than prior sampling or rejection sampling, because prior sampling can reject samples and rejection sampling can also generate samples and then it needs to reject them if they don't comply with the evidence. Whereas likelihood weighing uses all the samples. So this gives us a concept called sampling efficiency. Sampling efficiency is the number of samples or the amount of work an algorithm needs to do in order to approximate a value within some error tolerance. Sample efficiency can be used to compare algorithms. We prefer an algorithm that does less work to approximate a value. And so if we have a query, the probability of Q given some evidence, and we have some options, we can use prior sampling to solve this. We can use rejection sampling, or we can use likelihood weighing to answer this query. So which of these queries is more sample efficient? In other words, which of these queries does the less amount of work? Remember, prior sampling can generate n samples, but many of them may be discarded. And so in practice, I may use less samples than what I generated. Rejection sampling will generate n samples, but in order to generate all n samples, maybe some of the samples as I was generating need to have been discarded, right? Whereas likelihood weighing, every sample I generate will be consistent with the evidence. So you already see that likelihood weighing is the most sample efficient, followed by rejection sampling, followed by prior sampling. And so when we say algorithm A is more sample efficient than algorithm B, we are saying that A uses less samples than B to achieve the same tolerance. And so rejection sampling is more sample efficient than prior sampling. Likelihood sampling uses all the samples, and so it is more sample efficient than prior sampling and rejection sampling. However, likelihood weighing still degrades as the number of evidence variables increases. So it is this is less severe than rejection sampling. So what I want to say by degrades is that we mean that to get within the specified tolerance, more samples are needed as the number of evidence variables increases. So it is not the most sample efficient algorithm we know. There's actually more sample efficient algorithms than likelihood weighing or likelihood sampling. These are MCNC and Gibbs sampling. These are the two algorithms that we didn't discuss, and we don't really cover it in this course, but I thought to mention it so that you are aware. Going back to the PGM-PY package, as I mentioned, this supports Bayesian networks. It supports exact inference, but it also allows you to run approximate inference as well. And you can use rejection sampling, and it also supports likelihood weighing sampling as well. And with this, we have finished the uncertainty topic. وجزاكم الله خير. والسلام عليكم ورحمة الله وبركاته.